is chapter 10.6, 10.7, the first part. So we're going to kind of split this lesson into two parts. And start with kinetic energy of rotation. If we have something rotating, we can kind of think of it as each part of that thing going around. So what would the kinetic energy be of each individual part? Well, that would be like the mass of each individual part times the square of the velocity and then half of that. So k equals 1/2 mv squared. And then for each individual part, so we've got 1/2 mi vi squared. But we know that v is r omega, so we kind of split that up. So now we've got 1/2 mi ri. So r is, the radius from the center of rotation to that particular point. R squared, omega squared. And so what we end up with is the kinetic energy. Then we add all those up, so we have the sum. And the kinetic energy of the whole thing is the 1/2 times the sum of all the masses times the square of their radii, and then that times the square of the rotational velocity. And the rotational velocity is the same for all of them, so that kind of gets factored out. If we take mr squared and we call that I, the sum of mr squared. And I is the rotational inertia of the object. That is, if we're kind of translating between linear and rotational. In linear dynamics, we have mass. In rotational dynamics, we have moment of inertia. And the thing about moment of inertia is that it depends on the axis about which we're rotating. So the subscript next to I, you always see I and then some subscript. Same thing for K, and then some subscript. That's telling you the axis of rotation for that particular moment of inertia or for that kinetic energy. Okay. Notice the units for kinetic energy. It's the same as it is in the other one, joules. And then it can be converted between linear and rotational, and we're going to see problems like that. And also the units of moment of inertia is kilograms meters squared, because we calculate it as mass times the square of the radius. And so, think about if regular inertia is mass, and that indicates the resistance of acceleration of some object, how much that object resists accelerating, then moment of inertia is an indication of an object's resistance to accelerating in its spinning. If I have something, I'm spinning it around. And so if I have an object that I'm trying to spin, this one's pretty easy. And if I put two weights on the ends, it'll be kind of hard to spin. But if I put two weights in the middle, close together, it's easier. It makes it easier to spin it. The further out those weights are, the larger the moment of inertia. And we can see that in the r part of that, right? mr squared. The bigger r is, the larger that moment of inertia. Whereas if the things are close together, then that makes the moment of inertia smaller. And you can see the example there of a tightrope walker. They had these long poles. Why? Large moment of inertia. So if they start to fall, they can pull on that pole. It has a large moment of inertia, and they can correct themselves, and that'll help them balance. Okay, so for this question, we're asking, where is it easiest to balance the hammer? Like this or like this? And actually, the answer is that it's easier here because the moment of inertia is bigger. Since it has a larger moment of inertia, it'll take longer to fall over. As opposed to like this, it has a lower moment of inertia, right? Is smaller, so it'll accelerate more quickly, and it's harder to catch. But like this, it doesn't accelerate, it doesn't rotate as fast from the force of gravity that pulls on any imbalance in the hammer, and I can move my finger to adjust more easily. Question 2, we have a meter stick with weights placed at the ends. And the question is, where is it going to be hardest to spin this, and where is it going to be easier? So in other words, if I hold it at A and I try to turn this really quickly, is that going to be easier or harder than holding it at C? And the answer is it's going to be easiest to spin this if I hold it at A, because there I'm close to the center of mass. The two ends kind of balance each other out, and so I have a smaller moment of inertia than if I was at B or even C. At C, it's going to be harder for me to spin this, to take it and turn it and accelerate it really easily because of this weight that's really far away that's not being balanced out by anything over here. So it's easiest to spin at A, it's harder at B, but it's hardest to spin if you're holding it at C. All right. In example 1, you have two spherical, nearly point masses of 5 kilograms each, and they're connected by a light, massless rod in our magical physics universe, which is 1 meter long. So you've got the drawing down there, so you can kind of label it, half a meter, all that stuff, 5 kilograms. The system rotates about the center of mass. So calculate the moment of inertia of the system. Okay. So for letter A, since I'm going around the center of mass, I'm going to write ICM. Remember, the subscripts tell us where I'm rotating around. And so what am I doing? I'm adding up all the masses times the square of their radii. And so this is going to be, I've got 5 kilograms times 0.5 meters squared, right? That's one of them, plus the other one. So you're adding this up, or you could just do 2 times this, right? It's symmetric. They're both the same distance from the center, half a meter. And so when you add all this up, you get 2.5 kilograms kilograms square meter. Okay. And then for 2, so this is A1. A2, it wants us to find the kinetic energy of the system if it rotates at 2 revolutions per minute. Right? Notice that RPM stands for revolutions per minute. It's like in cars and stuff, something's rotating RPMs. And so we want omega though, right? K is 1/2 I omega squared. So how do we get omega? Omega is in radians per second, not revolutions per second. And so let's see. Let's do the conversion. 2 revolutions per minute. Let's see, RPM, revolutions per minute. But I know I have 2 pi radians for every 1 revolution, right? So you get revolutions to cancel out. And then I know I have, in every 1 minute, there are 60 seconds. So minutes cancels out. So 4 pi over 60 is going to give me 0.21 radians per second. Right now I've converted to radians per second. I now have omega, and I can do this calculation. So K, the rotational kinetic energy around the center of mass, is 1/2 I omega squared. So we plug in our numbers. 1/2 I is 2.5 kilogram square meters times 0.21 radians per second squared. Okay, that comes out to about 0.0506. What about the units? Is kinetic energy also different from linear kinetic energy in rotation in terms of the units, like with theta and alpha? Well, if we look, kilograms meters squared, and this is over seconds squared. So a kilogram meter squared per second squared is a joule. So kinetic energy is measured in the same units, whether it's rotational or linear. Right? And we're going to see that conversion taking place in some problems that we do later. Okay, and now B. What I'm doing is I'm rotating it around the center of one of the spheres. So if this is what it looks like, now I'm going to take this thing and I'm going to rotate it around this. So this whole thing is spinning around. This is like the question that we just had in the previous slide about the ends, the weights on the end of a meter stick, right? Where do I put this? So we're going to see that the I is less in the first case. I'm going to call this axis that's going through there, OO. Okay, so I00 or IOO is going to be adding up all the masses multiplied by the square of the radius. And so this will be, this is 5 kilograms, okay, times 1 meter squared plus, that's this one. This one is 5 kilograms, but it's at 0 meters squared. 0 meters. So that one just goes away. And I'm left with having an I of 5 kilogram square meters. Notice that's more than the one in part B, or part A, I should say. Okay. For part 2, the rotational kinetic energy around point 00 is 1/2 I omega squared. Again, same thing, 2 RPM, so I can use the number that I got for part 1. And this is 1/2 5 kilogram meter squared times 0.2 1 or 209 radians per second squared. And you get 0.109 joules or something close to that, depending on how many decimal places you've taken on that. So C, where is the moment of inertia least? Around the center of mass. Always the moment of inertia is less around the center of mass, because if you can think about it that way, then you've got equal weight on both sides, balancing everything out. It's a little bit easier to turn something that way. It's a little bit less resistive to acceleration. Okay, now let's take a look at example 2. In example 2, we have something that looks kind of like this. You can see these things. So what's going on here? We've got the rod and 2 masses here, 1 mass on either side, like that. That's what we have illustrated. And in our diagram, it looks like this. This is 1, this is 2, 1, 2. This is supposed to be 3, 3, 2, 2. Those distances, meters and kilograms. Obviously, this is not 3 meters and kilograms and all that stuff. But you can see we've got 1 block on top, 1 block on the bottom, like 1 and 1, and 2 and 2. So now we want to know, what is the rotational inertia about the z-axis? Well, if we're holding it like this, the z-axis is the one that comes out like this, right? So we're talking about rotating it this way. What is that rotational inertia? So going around the z-axis, IZZ, we're going to specify around the z-axis, is, let's see, I've got 2 1 kilogram masses, 2 1 kilogram times, and they are 2 meters from the edge. And then I've got these 2. So I've got 2 of these, the 2 over here. They're both 2 kilograms, and they're both 3 meters from the center, from the axis, through the middle there. And so when I add all these up, I get 44 kilogram square meters. And now through the x-axis. The x-axis, if I'm holding it, would be through here. Right? So that would be like spinning it like this. I don't know, what is that moment of inertia if I'm trying to spin it around the x-axis? So around the x-axis, these 2 weights are on the x-axis. So those actually just, I ignore those. I don't even pay attention to those. These, however, are not on the x-axis. These are 2 meters from the x-axis. And I've got 2 of those. So 2, 1 times 2 squared. And you can see that gives me 8 kilogram square meters. Now what about going around the y-axis? Around the y-axis, that's me holding it like this and spinning it around this axis here. How is that any different? When I'm holding it like that, these 2 masses are along the axis. These are 0 meters from the y-axis. And as a result, I ignore those. So I, y, y, all I care about are these 2. So 2, they're each 2 kilograms, and they are 3 meters from the edge. I think you get 36 kilograms square meters. Okay. Notice this one is more than this one. This one, I've got the 2 little weights, and they're a smaller distance. Here, when I'm spinning around the y-axis, I have the 2 heavier weights, right, and they're farther away. So I would expect this moment of inertia to be less than this moment of inertia. And don't forget, since they're point masses, I don't care about what it takes to get this thing rotating. They're point masses, so if they're points, they are infinitely easy to get rotating, which is not physically possible. And even though this is physics, we don't care. Okay, so the next question, D, what is the relationship between A, B, and C? Well, if you notice, this is this, and this is this. So the result that I get, interestingly enough, is that IZZ is equal to IXX plus IYY. When I add these two up, I actually get that one. Okay, and now for part E. Part E now, what I'm doing is I'm finding out if I rotate it around one of the 2 kilogram spheres perpendicular to the x-axis and parallel to the z-axis. So that means I'm actually rotating it like this. Here's the z-axis, right? Like this. So I'm perpendicular to that, or parallel to this, but perpendicular to the x. This is x, perpendicular to that, but where? Here, so that it's parallel to the z-axis. This is the z-axis, so I'm rotating around here like that. Okay? So I'm going around this axis that's coming out the side here. So I need to add up these masses. This particular mass I don't care about. So I'm going to call this axis OO. OO. So IOO is the distance from here to here. This is 2 times, and the distance is 6. So 2 kilograms times 6 meters squared. Plus, and now I'm going to have 2 of these, right? 2, this one and this one. But what's the distance now? The distance is this. So I need to take 2, 3. It's not a 3, 4, 5 right triangle. I apologize. We usually like to make that easy if we can. 2 squared plus 3 squared gives me 13. So 2, they're each 1 kilogram, and they are the square root of 13 meters. Square that. And so what I end up with is 98 kilogram meters squared. And then F, what happens if I go around an axis that is parallel, so perpendicular to the z-axis again, so that means I'm somewhere here, but parallel to the y-axis, right? So that would mean I'm going around this axis like this. And in my drawing, that would be a vertical axis like that. Okay. And what do I call this? Let's call this QQ. All right, so IQQ. All right. I don't care about this mass because it's it's along the axis. It's no distance away. This one, though, 2 kilograms times 6 meters. I square that. Plus, and now these masses, the 1 kilogram masses are actually, they're each 3, right? I go directly from here to the Q axis, and it's only 3 meters away. So I have 2 of these that are each, 1 kilogram, and they are each 3 meters away. And the answer that I get for that now is 90 kilogram meters squared. This one is a little bit less than this one because this distance is a little bit less than this distance, right? This one, it's that distance, but here I'm looking at just this distance. And so that's why this moment of inertia is a little bit less than that one. This now is a preview of the parallel axis theorem. And that is coming on the next page, just like your result for question D is the plane figure theorem, which is the next slide. So now let's talk about the plane figure theorem. Really, we just saw that in example 2 with looking at, IZZ equals IXX plus IYY. That was the result. But here's the thing. this only works for plane figures. So for example, something like this, right? This is a plane figure because it, for our purposes, exists in one plane. So if you were to take, the moment of inertia around this axis and the moment of inertia around this axis, you add those up, that gives you the moment of inertia around this axis. Okay, so be careful in the way you use it, but we will use it, and it's going to be really useful when we're dealing with, two-dimensional figures like this, or even like that example of the blocks at the ends of the two poles. And the parallel axis theorem, we just saw that with the results of E and F. If we take E and F and compare those results to the previous ones, what you'll find is that we're taking the moment of inertia around the center of mass and around a particular axis, so parallel to the x-axis or parallel to the y-axis. And what we've done is we've taken the original one around the center of mass, and if we add that same mass plus the square of the distance from the axis, then that gives us that new moment of inertia. And that's called the parallel axis theorem. And that's going to be really powerful as well, because we're going to memorize the moments of inertia for certain objects. And then if we want to find the moment of inertia around a different axis, we can just use the parallel axis theorem. So make sure you know and can use those theorems easily. And so that's where we're going to end for this particular lesson, 10.5 and 10.6. And we'll continue the lesson with continuous mass distributions in the next video.